This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2017 AP Calculus exam free response question BC6. My name is Steve Kokoska, and I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions presented in these guidelines, not how the points were awarded. Even though this question was not calculator active, I'll show you how to use technology to explore and solve parts of this question, where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some additional extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. In this problem, the function f has derivatives of all orders, and the derivatives satisfy certain given conditions. And the Maclaurin series for f converges to f of x for the absolute value of x less than 1. In part A, we need to verify the first four non-zero terms of the Maclaurin series and write the general term for the Maclaurin series. In part B, the student needs to determine whether the Maclaurin series in part A converges absolutely, converges conditionally, or diverges at x equal 1. In part C, the student needs to write the first four non-zero terms and the general term of the Maclaurin series for a new function g, defined as the integral from 0 to x of f of t dt. And in part D, the student must use the alternating series error bound associated with the Taylor polynomial for g about x equals 0. Part A was worth 3 points. 1 point for finding the second, third, and fourth derivative of f at x equals 0. 1 point for verifying the first four terms. And 1 point for writing the general term of the Maclaurin series for f. Part B was worth 2 points for stating that the specific series converges conditionally and for providing an appropriate reason. Part C was worth 3 points. 1 point for correctly writing any two of the first four non-zero terms of the Maclaurin series for g, and 1 point for the remaining two terms, and 1 point for the general term of the Maclaurin series for g. Part D was worth 1 point for using the alternating series error bound to verify an inequality involving the fourth degree Taylor polynomial for g about x equals 0. Even though this question was not calculator active, I'm going to show some ways to explore and confirm the solutions. In part A, I'm going to use a TI-Nspire lists and spreadsheet page to find the second, third, and fourth derivatives of f at x equals 0. I used a general sequence command to generate these values. And in this column, I found the first four non-zero terms of the Maclaurin series. Now, I could generate even more derivatives and specific terms of the series to help with pattern recognition, and to write the general term of the series. Students are probably pretty familiar with the harmonic and alternating harmonic series. But here, I'll use technology to produce a graphical representation of each. First, for x equal 1, the Maclaurin series in part A becomes this series. And this is the alternating harmonic series, and it converges by the alternating series test. Here's a graph of the terms of this sequence and the partial sums. This is a nice visual confirmation that this series converges. And if we consider absolute convergence, the series becomes the harmonic series, which diverges. And here's a graph of the terms of this sequence and the partial sums. Again, I think this is a nice visualization to suggest that this series diverges. To emphasize the rule of 4, I'm going to consider a numerical approximation to the sum of each series in order to help me explore and confirm the convergence or divergence results. On a TI-Nspire lists and spreadsheet page, I found the partial sum of each series for various values of n. This column corresponds to the alternating harmonic series, and students might recognize this numerical value. And this column corresponds to the harmonic series. And just because I'm using a CAS machine, I think it's pretty cool that I can actually find the exact symbolic partial sum of each series. Well, here at least for the first 50 terms. Here's a problem extension to this free response question. In this example, let's find the radius and interval of convergence of this Maclaurin series. Now, this is a pretty common type of question on BC6. So one purpose here is to suggest a general prescriptive solution method. I'll be using the ratio test, but I'll split the process up into two parts. First, I'll find and simplify the absolute value of the ratio a sub n plus 1 divided by a sub n. Next, I'll consider the limit as n goes to infinity of this simplified ratio, and the limit is the absolute value of x. So, by the ratio test, this series converges if the absolute value of x is less than 1, and diverges if the absolute value of x is greater than 1. And therefore, the radius of convergence is r equal 1. To find the interval of convergence, we need to consider the endpoints of this interval minus 1 to 1. For x equal 1, the series becomes the alternating harmonic series, which converges. And for x equal minus 1, the series becomes a constant times the harmonic series, which diverges. And therefore the interval of convergence is minus 1 open to 1 closed. Here is an example of how technology can help with this solution. On a TI-Nspire calculator page, first define the nth term of the series. Then find the absolute value of the ratio a sub n plus 1 divided by a sub n. And then find the limit. Now, of course, one can find the limit in just one step, but my preference here is to break the solution into smaller, manageable, understandable parts. In part C of the free response question, I can use technology to find the first 4 terms of the Maclaurin series for G. On a TI-Nspire calculator page, I defined a function f, which is the first 4 terms of the Maclaurin series for the function f in the free response question. And then I simply found the definite integral of my f from 0 to x. Note that the calculator answer here is not in the form that I'd like. So there's still a little analytical work to present the first 4 terms of the Maclaurin series for G in an appropriate form. Here's another problem extension. Let's consider the function f defined by its Maclaurin series. Now, we already know the interval of convergence for this series. However, let's find the interval of convergence for the integral of f, and find the interval of convergence for the derivative of f. I'm going to leave the solution of this example to you. However, I do want to remind you of an often overlooked theorem related to this example. Suppose we have a power series for the function f with radius of convergence r. What's the radius of convergence for the derivative of f and for the integral of f? And what's the interval of convergence for the derivative of f and the integral of f? These results will certainly help in solving example 2 and on similar AP Calculus exam series questions. In Part D of this free response question, I can use technology to find a bound on the error, here the magnitude of the first unused term. Again, breaking this solution into parts, I defined a function b, which is the nth term of the series. Note that b is a function of two variables, n and x. I then found the absolute value of the fourth term. Now, to finish the solution to this problem, I'd really like my students to confirm that this value is less than 1 divided by 500. Here's one more problem extension. Consider the function f defined by its Maclaurin series. First, use this Maclaurin series to approximate f of 0.5 to 6 decimal places. Find a closed form expression for f of x. And use technology to sketch a graph of this remainder on the interval minus 0.5 to plus 0.5. I think this graph is another way to visualize a Taylor polynomial. So justify the general shape of this graph. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions, and of how to use technology to solve some of the parts of this problem, to explore, confirm, and visualize results. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.